Hello everybody and welcome to lecture 3 where we're going to talk about amplitude modulation. So this is the second in our series on modulation where we introduced modulation. Today we're going to talk about amplitude modulation, and next week we're going to be looking at amplitude demodulation, and then these two lectures are specific types of amplitude modulation that we'll be looking at in more detail in lectures 5 and 6. So again, just as a reminder, there's a class test on March the 17th, so make sure you have that in your diary. So that class test will include all the material from the start until the end of lecture 6. So again, the class test I was talking about is on the 17th of March. We are now in week 3. So that's today's lecture, and we will be meeting on Wednesday for the problem class, the Kahoot on amplitude modulation. There is also a problem sheet, but we won't be going through this together. The problem sheet has associated pencasts, and you're welcome to read that in your own time during the week. Okay, we will be looking at problem sheets together, but that's in the catch-up week in March. So Wednesday the 10th of March, that's the week just before the class test. We'll be looking at any issues you might have had in the problem sheets. Again, I'd just like to remind everybody to do the weekly progress check. So don't leave it until the last minute. Do the weekly progress check as soon as you can. So as soon as you finish listening to this lecture, go to the progress check and answer the question. It's one question, as you know, but you need to have done that by Sunday midnight. Okay, and this is our second class test. And that comes right at the end of the semester in week 11. Okay, so last week we introduced modulation, and in doing so we spoke about some things which happen to the signal in the channel. So we spoke about channel bandwidth, and then we spoke about these three things: noise, interference, and distortion. And on the subject of noise, we introduced the idea of signal-to-noise ratio, and we actually quantified it. We said signal-to-noise ratio is 10 log the ratio of the power of the signal noise to the power noise, and the unit is in dB. So that's one thing we looked at. We had a look at the electromagnetic spectrum, just so that you can appreciate that the carrier frequency, the frequency of the carrier, is much bigger than the frequency of the message. We spoke about different regions of the electromagnetic spectrum for low frequency, medium frequency, high frequency, UHF, and then frequencies dedicated to 3G, 4G, Bluetooth, Wi-Fi, and things like that. And we answered a few questions in the problem sheet about frequency ranking. Then we introduced 2 or 3 reasons why modulation was important, and we introduced some of the types of modulation. We said, in its simplest form, modulation is a shift in frequency that enables a message signal to be impressed upon or encoded within a carrier signal of a higher frequency. So that encoding could be in the amplitude of the carrier, or it could be in the frequency of the carrier. So if we encode the message into the amplitude, we call it amplitude modulation. If we encode it within the frequency, we call it frequency modulation. There's also something called phase modulation, which looks very similar. And amplitude modulation comes in 4 or 5 different variants, which we'll introduce in the coming weeks. There's also a problem class 1, which was mainly a Kahoot class, and that is available as a recording. It's also available as a Kahoot challenge for you to take the questions in your own time, or you can simply read through the questions. That's the least helpful way to do it, but it's available to you if you so wish. So, you'll remember this slide from last time. We said when we transmit information, we have a high-frequency carrier, and that's generated at the transmitter. And somehow we modulate that carrier with some information. That information can be analog, and that's analog modulation, or digital, and that's digital modulation. So we're going to be looking at this later in the semester. So it'll be lectures 10 to 12. So lecture 9 will be looking at digitization, and then digital modulation all comes in the last few lectures. So demodulation is where we try to detect the changes that have been made to the amplitude or the frequency in order to recover the original message again. So, remember we said there's analog and digital. So today we're going to be talking about a particular type of analog modulation, which is amplitude modulation. Now, I said amplitude modulation comes in a number of variants. Today we'll be looking at this, AM. So AM doesn't stand only for amplitude modulation. It stands for a particular type of amplitude modulation, which we call double sideband large carrier. So DSB-LC stands for double sideband large carrier. The week after next, we'll be looking at double sideband suppressed carrier. So that S is for suppressed. We'll then look at single sideband and vestigial sideband. All of these are forms of amplitude modulation. We'll then look at angle modulation, which includes FM and PM. Then, as I said in lecture 10, we'll be looking at digital modulation. So let's make a start. Today we're going to introduce AM. We're going to introduce something called the modulation index, or the depth of modulation, and we'll look at what it looks like in the frequency domain, so the spectrum. Next week, we'll look at the opposite of modulation, which is demodulation. So we'll look at one of the ways that we can recover the original message signal from the band pass modulated signal. This is just a word cloud created from my lecture notes, and you'll see that there's a lot of emphasis on spectrum, signal, sideband, and power. And power is something that we'll speak about in a lot more detail next week. So, when we talk about amplitude modulation, as I said, there's DSB-LC, which we're going to talk about today, but there's also DSB-SC, or sometimes just DSB, and that's something we'll be talking about in lecture 5. SSB, single sideband, and vestigial sideband also. This is all material we'll be covering in lecture 5. So, whenever you see AM, it will generally, but not always, refer to DSB-LC, and that's what we're going to talk about today. So, basic amplitude modulation, what do we mean? So, you have some baseband message. Okay, so a message is almost always going to be baseband. So that could be somebody's voice. So that signal is captured by some sensor, a microphone in this case, and something happens in this box, this modulator, where this signal is mixed with a high frequency carrier. So this is your carrier. Your carrier signal contains no information. It's simply a high frequency signal. Something happens in here, and you have your message somehow, so the baseband message, the voice signal, is somehow encoded within the amplitude or the envelope of the carrier. So the carrier has been changed. All right, so in the actual PowerPoint, this is an animated GIF. So here you have your modulating signal, so that's this. Here you have your carrier, which is this. Something happens in here, and you have your modulated signal. So your modulated signal, this is your band pass signal. So this is the signal that's actually transmitted. Again, this is a useful little YouTube video that in a live lecture I would have actually played for you. It's only a few minutes long. I suggest you do listen to it. It's nothing new. It doesn't add anything to this lecture, but it's a nice set of illustrations. So let's try to look at this mathematically. Let's imagine that we have a baseband message that isn't somebody's voice, but it's actually a single tone signal. Single tone signal. What does that mean? It just means that we have a pure sine wave. So sine, cosine, same thing. So we have a pure sinusoidal signal. So this is our signal. It's baseband. That means it's low frequency. Nothing's happened, hasn't been modulated yet. And we have a high frequency carrier. So that was our message. Here we have our carrier. So it's a high frequency carrier. What do I mean by that? I mean that omega C is much larger than omega M. So here, omega C is much larger than omega M. It's not just larger, it's much larger. This message contains information. This carrier contains no information. It's simply a constant amplitude, high frequency signal. Something happens in here. We call that process modulation. And what that gives us is a modulated signal, where the signal has actually modulated, i.e. it has altered, it has changed, it has encoded itself within the amplitude or the envelope of the carrier. So this is modulated. It's called a band pass signal. It's ready for transmission. So that pink bit is called the envelope. So again, mathematically, if our message signal was a simple cosine and our carrier was a simple cosine, and the only difference was that FC was much larger than FM. We also have two amplitudes that don't really matter yet. Now, something happens between the two in order to produce this. And that something consists of a multiplication that's happening right here. That's your multiplication. And here you have a DC shift. Why do I call it a DC shift? Because you're adding something. You're adding a constant value to your message. So remember, this bit is simply your message. So your message is being DC shifted. What do we call a DC shift? Remember we called that clamping? So that bit is clamping. And this multiplication, that's modulation. Together, that creates amplitude modulation. So this message is first clamped. That means it's raised. And that is then multiplied by your high frequency carrier. And that'll give you this signal here. And this is your band pass AM, where the signal is actually encoded there within the envelope of the carrier. So, I want to introduce something called the modulation index, or the depth of modulation. That determines how deeply we impress this signal on the carrier. So you could impress the signal very lightly or more deeply. So this depth of modulation is determined by something called the sensitivity, or the modulation index. We'll be using the term modulation index, M. And our modulation index can be 0, can be greater than 1, can be 1, or can be less than 1. And I'll explain what each of those means. So if the modulation index is 0, then there is no modulation. And if I remind you of what that means, it means that here you would have 0. Your message will be multiplied by 0. So you'd only have the carrier. So that would be carrier only. If the modulation index is 1 or 100, we call that 100% modulation. If the modulation index exceeds 1, we call that situation overmodulation. And we always try to avoid this situation. Overmodulation is something we must always avoid. And the reason is because the more you modulate, the closer these two get together. Until at some point, if you exceed 100%, what you'll have is a phase reversal. And then it will be impossible to trace the envelope in order to recover the message. And we'll speak about demodulation next week, but this week I just want to make the point that the modulation index shouldn't be 0, it cannot be negative, and it shouldn't exceed 1. So we want the modulation index to be as high as possible, but shouldn't exceed 1. All right, so a little bit more illustration. When you modulate, you end up still, we're assuming we have a single tone AM. So here you have your envelope, and if you look at this maximum value and this minimum value, so you have your maximum envelope value, your minimum envelope value, you can find the difference of the two. And if you divide that difference by the sum of the two, that gives you your modulation index. So that's a nice, quick way to find your modulation index. It's dividing the difference between the maximum envelope and the minimum envelope, dividing it by the sum of the maximum envelope and the minimum envelope. So, quick question for you. Looking at this signal here, can we find the modulation index? So remember, the modulation index is the ratio of the difference, so it's A max minus A min divided by A max plus A min. That's the modulation index we're after. So if you look at it, A max looks like it's 5 and A min is 2. So that's the maximum envelope, and this looks like it's the minimum envelope. So it's 5 minus 2 over 5 plus 2. So that's your modulation index. And we found that simply by inspecting the amplitude. We didn't need to look at the frequency at all. Now remember, we said the modulation index should always be greater than 0 and less than or equal to 1. Now if the modulation index ever exceeds 1, we then end up with something called overmodulated AM. So that's when M is greater than 1. So oversampling, remember, wasn't a big problem, but overmodulation is a problem. And the reason, as you can see, is we can no longer recover the message by tracing the envelope. We have a phase reversal happening here and here. So it means that if we try to recover the signal by tracing the envelope, we recover a distorted version of the signal. That distortion is undesirable. Remember, we said desirable characteristics of a communication system are that the recovered signal or the received signal should be as close as possible to the original signal. We call that high fidelity. So if you overmodulate, so if M is greater than 1, we have these phase reversals. These phase reversals result in distortion. That means your recovered signal doesn't resemble your original signal. So this doesn't look like that. So that's undesirable. We want to avoid such a situation if we can. Now, last thing we want to talk about in this lecture is the appearance of AM in the frequency domain. So what does the spectrum of AM look like? And I remember I said we're going to be looking at frequency representations a lot this semester. So everything we covered in signals and systems about the frequency domain becomes very important. So if we take the mathematical expression for AM, where is it? If we take this mathematical expression for AM and expand it, if we go back here, if we take this and expand it, if I multiply the cosines, you'll have a cosine, cosine, and using the identity that the product of two cosines gives you the sum of the cosine of the sum and the cosine of the difference. So that gives us cosine of the sum, cosine of the difference, and this is simply the carrier multiplied by 1. So my band pass AM signal looks like it has 3 components. 1, 2, 3. The first component is simply the carrier. That's simply this. This second component is a frequency component at frequency omega c plus omega m, where omega c is the carrier frequency and omega m is the message frequency. Okay, so omega c is 2 pi fc and omega m is 2 pi fm. So we call this the upper sideband. We call this the lower sideband. And we call this the carrier component because it is a component at the carrier frequency. So that's what AM looks like in the frequency domain. That's the spectrum of AM. But it's a very specific type of AM. It's single tone AM. That means there's only one sine wave. Our message is the most boring message in the world. So our message was simply, so M of t was simply AM cosine omega mt. That was our message. Very boring. It doesn't consist of anything. It's just a single tone. That's why it's a single tone. In reality, in real life, we don't have messages that boring. What we have is messages that maybe look like this. We have a real spectrum, so not just a single impulse, omega m and minus omega m. What we have is a range of frequencies. So if this was my voice, for example, if this was my voice, then that FM would be something like 4,000 hertz. Okay, so this is our baseband signal. This is our baseband message. Notice that the frequency axis has a positive side and a negative side. And I'll try always to represent things on both sides, even though they are the same. So the positive frequency has a tangible physical meaning that we understand. Negative frequency doesn't, but it is a mathematical reality. So remember we said for a baseband signal, the bandwidth is equal to the highest frequency component. That's your bandwidth. So your bandwidth is that range from 0 up to the highest frequency component. It doesn't matter whether the spectrum starts from 0 or not. What matters is because it's baseband, we always start from 0. We always measure from 0. So the bandwidth is equal to FM. So in the case of my voice, it would be 4,000 hertz. Now, after amplitude modulation, we go from bandpass to baseband. Now, remember a second ago, our spectrum looked like this. Really boring. Carrier component, upper sideband, lower sideband. This time, slightly less boring, but it's the same. I still have a carrier component, but the upper sideband isn't just a simple impulse at FM and another impulse at omega c minus FM, but it's the whole spectrum. This whole spectrum is shifted here. So we have 1, 2. This is the upper sideband, and this is the lower sideband. And we find that this is mirrored in the negative side of the frequency axis. So we have the carrier, we have the upper sideband, so this corresponds to that, and we have the lower sideband, so this corresponds to that. But notice that the total bandpass bandwidth, that's this total bandwidth, this total bandpass bandwidth, the bandwidth of the AM signal, is actually this plus this, which is twice FM. So the bandwidth of my original signal was FM, the bandwidth of my bandpass signal is twice FM. So if this was 4 kilohertz, this would have been 8 kilohertz. Right? So the bandwidth of AM is twice the bandwidth of the baseband signal. So here I've called it a continuous spectrum as opposed to a single tone spectrum. Okay, so that's all I wanted to cover today. Just as a summary, what have we covered today? We've mentioned that carrier frequencies have much higher frequency than the baseband signal. Generally, baseband signals for voice at least, and for AM, is generally in the region of 10 kilohertz. And rather than voice, let's say for audio, so for sound. Whereas the carrier is more than 50 times, all right? So we're talking about 500 to 1,600 kilohertz. That's the range for amplitude modulation. So if you look at that, we're talking about times 50 to times 160. We mentioned that the message signal is encoded in the envelope of the carrier. We spoke about overmodulation, and we spoke about the modulation index being always less than or equal to 1. We said the bandwidth of your bandpass signal is twice the bandwidth of the message. All right, so that's 2 times FM. We said that the spectrum actually contains a carrier component. So there's always a carrier component. Either we have a spectrum that looks like that, or we have a spectrum that looks like that. Okay, it can look whatever your message actually looks like. It could look like that. But whatever it is, the bandwidth will be this total. So that's 2 times FM. This is your upper sideband, and that is your lower sideband. And that in the middle, that's your carrier component. And because we have a carrier component, we call this DSB-LC. That stands for double sideband. That's 1, 2. That's the word double. Double sideband with large carrier. That's a large carrier. It actually exists in the spectrum. So all modulation involves the carrier, but not all modulation schemes will have a carrier component in the spectrum. Okay, there's a couple of apps I wanted to show you. These are sort of visualizations. They're not apps. Let me see if I can show you. So these links should both work, and these QR codes are shortcuts to the links. Let me see if I can show you this. So this is a nice little demonstration where you have at the top, the blue signal is your carrier signal, and the red signal is your message signal. And what I can do is I can change the carrier frequency, and you can see how the AM signal, which is the signal at the bottom, actually changes. So I'm going to increase the carrier frequency, and I'm going to increase the message frequency. So that's high frequency, low frequency. So you can see that I'm changing the message, which is the red signal, and that's changing the shape of the modulated signal. And I'm now going to change this third slider, which is the amplitude. So I'm changing the amplitude of the red signal. So what I'm also doing is changing the depth of modulation. So that's a modulation index. So if I bring it to 0, it's as if there's no modulation. I simply have the carrier. As I increase the amplitude, the depth of modulation increases until I get to a point where at modulation index of 100, the upper and lower envelopes touch each other. So if I were to increase the amplitude any further, if I was to increase the modulation index any further, the envelopes would overlap, and then it would be impossible to recover the signal using an envelope detector. So that just shows you that. And there's a nice little, you can actually listen to the frequency as I change the carrier frequency and as I change the message frequency. What we're listening to here is the composite signal, i.e. the AM signal. So that was one of the demonstrations. This other one, if I can just get it to fit on the screen, is slightly nicer actually, because it shows you the frequency domain representation. It shows you the time domain and the spectrum. So what you can see, the red signal, that's your baseband signal. The blue is your AM signal. So see what happens as I change the frequency. I'm going to move that slider, and hopefully when I do so, as I change that frequency, let me see if I give that a refresh. Yeah, so as I change the frequency, that changes the position of your impulses in the spectral plot. All right, so it's a bit slow, but there, as I change the frequency of the red signal, you can see it moving from the left to the right. And as I change the depth of modulation, look what happens is, to the relative amplitudes of the sideband and the carrier. So that's 100% modulation. So 100% modulation, the amplitude of the carriers are each half the amplitude of the, the amplitude of the sidebands are each half the amplitude of the carrier. Whereas if I were to reduce the depth of modulation, the sidebands diminish. They become much less powerful compared to the carrier. And you can see from the time domain plot that the depth of modulation is much less. So you can have a little play with that on your own. And also you can experiment with turning the carrier off and looking at single sideband, which is something that we'll be looking at in future lectures too. So that's a little demonstration for you to have a little play with. Okay, last question before we go. Here we're given the message frequency of 5 kilohertz and we've asked for the carrier frequency. So the message frequency is 5 kilohertz. What's the carrier frequency? Remember we said the carrier frequency is always much bigger than the message frequency. So that rules out 500 hertz immediately because the message is 5,000 hertz. It also rules out 5 kilohertz. That's just not possible. So really it's down to these two. And if you look at the time axis here, there's no annotation. We don't know what the frequency is because there's no scale. There's no annotation. So how can we find the carrier frequency? What do we do to find the carrier frequency? Well, the trick is to use what we do know. We do know that the message frequency is 5 kilohertz. That means that which is one period, that's one period of the message. Let's call it TM. So that's 1 over FM. And FM we know to be 5,000. So within that one cycle, how many cycles of the carrier do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 cycles or periods, 10 cycles of the carrier in one cycle of the message. So that means that TC is 1/10 of TM. You can do the maths and find FC, or you can say, well, it's pretty obvious from there that FC will be 10 times FM. So that's 10 times 5,000. and that's your answer. So we found the carrier frequency simply by measuring how many cycles of the carrier we had within one cycle of the message. Okay, so that was lecture 3 for you. What we looked at was the first of several types of amplitude modulation. We call this AM, or double sideband with large carrier. Now next week we'll look at how to demodulate that. So we'll be looking at demodulation of AM. All right, so that's what we looked at today, and next week we'll be looking at demodulation of AM. That's it for today. I hope you found today's lecture helpful. Do take a minute to complete this week's progress check and have a look at the problem sheets, and I'll see you on Wednesday for the problem class. So until we do, stay home and stay safe.